In chapter 11 of our course on linear system theory, we look at the singular value decomposition and induced norms. The first theorem, 11.1, defines what's called the singular value decomposition, or SVD in short. The singular value decomposition is defined for any not necessarily square matrix M, where we define R as the rank of M. Then there exist two unitary matrices, U in Cm by M and V in Cn by N, such that M can be written as U times sigma times V star, where the matrix sigma has a special structure as shown here. So it consists of a matrix sigma 1, 1 and zeros otherwise. And again, the matrix sigma 1, 1 looks as shown here. So it's a diagonal matrix which has R, real and positive values on its diagonal. And these values, sigma 1 through sigma R, are called the singular values of the matrix M. Note that by the fact that U is an M by M matrix and V star is an N by N matrix, this matrix here must be an M by N matrix, and sigma 1, 1 is obviously an R by R matrix. Moreover, the real and positive singular values can be arranged in such a way that they are ordered according to their magnitude. So sigma 1 is the highest singular value and sigma R is the lowest singular value, and all of them are greater than 0. For the proof of theorem 11.1, first observe that M star M is an N by N matrix, which is positive semi-definite. This is easy to see by picking any n-dimensional vector x and multiplying M star M from the left with x star and from the right with x, which is of course equal to the 2 norm of M times x squared, and this is always greater than or equal to 0. Moreover, M star M has the same rank as M, which is by definition equal to R, according to theorem 6.11e. Since M star M is positive semi-definite, by corollary 10.8 it has exactly R non-zero eigenvalues, and by theorem 10.12 these eigenvalues are real and positive. Or written in mathematical notation, if lambda 1 through lambda n are the eigenvalues of M star M, then we have that lambda 1 through lambda r are all greater than 0, and the rest of the eigenvalues, lambda r plus 1 through lambda n, are equal to 0. Moreover, since M star M is Hermitian, by theorem 10.7 it also has a full set of orthonormal eigenvectors x1 through xn. Since xi is the corresponding eigenvector to the eigenvalue lambda I, for any I from 1 to n, M star M xi is equal to lambda I xi, and therefore the 2 norm of mxi squared is equal to xi star m mxi, which in turn is equal to xi star lambda I xi, which by pulling out the scalar lambda I is equal to lambda I times xi star times xi, and by the fact that the xi are orthonormal, meaning that they have length 1, this is equal to lambda I. In other words, if we take the square root of this equation, we obtain that the 2 norm of m times xi is equal to the square root of lambda I, which is positive, whenever the index I is between 1 and r, and is equal to 0 for any index I between r plus 1 and n. Hence, for any I from 1 to r we can define sigma I as the square root of lambda I, which is a positive real number, and the vector ui as 1 over sigma I times m times xi, which is an m-dimensional vector because m is an m by n matrix. Observe that with this definition, for any two indices I and k in the set from 1 through r, we can write the product of ui star and uk as 1 over sigma I and sigma k times xi star mxk, which by the definition of the eigenvalue of m star m is equal to 1 over sigma I and sigma k times xi star times lambda k times xk, where we can again pull out the scalar lambda k, and by definition lambda k is equal to sigma k squared. So we get here that this is equal to sigma k squared divided by sigma I and sigma k times xi star xk. Now, with the fact that the eigenvectors are orthonormal, it follows that xi star xk is equal to 1 if I is equal to k and 0 otherwise. So therefore, we obtain for the product of ui star and uk that this must be equal to 1 if I is equal to k, and it must be equal to 0 if I is not equal to k. With this result, we have proven that the vectors u1 through ur forms an orthonormal set, which we can extend by using the Gram-Schmidt procedure by another set of vectors ur plus 1 through um, such that the entire set of vectors forms an orthonormal basis for the space Cm. Therefore, the matrix U, which we define as the matrix that contains the vectors u1 through um as column vectors, is a unitary matrix. And similarly, the matrix V, which we define as the matrix that contains the vectors x1 through xn as column vectors, is also a unitary matrix because, as we recall from the very beginning, the eigenvectors xi form an orthonormal set. Note that we partition the matrices U and V into U1 and U2 and V1 and V2 according to the first R eigenvectors, which correspond to the non-zero eigenvalues of m star m, and the first R vectors U1 through UR, which correspond to the non-zero singular values. And for convenience, we have stated here the dimensions of the partitioned matrices U1 and U2, and also V1 and V2. Hence, it remains to be shown that the matrix sigma, which was defined in the theorem statement, can be written as U star times m times V, which then clearly implies that m can be written as U times sigma times V star. And this last fact is proven by distinguishing three cases according to the following blocks of the matrix sigma, which is defined as U star mv. Namely, sigma can be partitioned into these four blocks, sigma 1, 1, sigma 2, 1, sigma 1, 2, and sigma 2, 2, which are given by these expressions according to the subblocks U1 star and U2 star of U and V1 and V2 of V. In the first case, which corresponds to the green subblock of the matrix sigma, we consider the index I between 1 and r and the index k also between 1 and r. Now we calculate the expression ui star mxk, where we first substitute for ui star 1 over sigma I xi star m star. where m star mxk is given by lambda k xk, which leads to this expression, and by the definition of lambda k as sigma k squared, we can pull out the sigma k squared in the front, and we obtain that this is equal to sigma k squared divided by sigma I times xi star xk. But again, the vectors xi are orthonormal, and therefore xi star xk is equal to 1 if the index I is equal to the index k and equal to 0 otherwise. Hence, it follows that ui star mxk is equal to sigma I if I is equal to k and equal to 0 if I is not equal to k. Written collectively, this means that the matrix sigma 1, 1 is equal to the diagonal matrix, where the values sigma 1 through sigma r are on the diagonal and all the other entries are 0. In the second case, we consider all indices I between 1 and m and all indices k between r plus 1 and n. And again, we look at the expression ui star mxk, where we can substitute ui star with 1 over sigma I times xi star m star. And then we can again substitute m star mxk with lambda k xk. But now this whole expression is equal to 0 because lambda k is equal to 0. And that's because, as you remember, all the eigenvalues lambda r plus 1 through lambda n of m star m are equal to 0. Written collectively, this implies that the blocks sigma 1, 2 and sigma 2, 2 are both equal to the 0 matrix. In the third and final case, we consider the index I between r plus 1 and m and the index k between 1 and r. Again, we look at the expression ui star mxk and we substitute ui star with 1 over sigma I xi star m star and m star mxk with lambda k xk, and with lambda k equal to sigma k squared and pulling the scalar into the front, we obtain the same expression as in case 1, sigma k squared divided by sigma I times xi star xk, where the vectors xi are still orthonormal, and hence xi star xk is always equal to 0, because for the given range of indices I and k in case 3, I can never be equal to k. Written collectively, this means that sigma 2, 1 is equal to the 0 matrix, and hence our proof is complete. From the proof of Theorem 11.1, corollary 11.2 is immediate. So for any m by n matrix M with rank m being equal to r, we have that m star m has exactly r non-zero eigenvalues, which are all real and positive and can be sorted as lambda 1 greater than or equal to lambda 2 and so on, greater than or equal to lambda r, which are all positive, so greater than 0. Then the singular values of m are given by the square roots of these eigenvalues. So sigma 1 is equal to the square root of lambda 1, sigma 2 is equal to the square root of lambda 2, and up to sigma r being equal to the square root of lambda r. The significance of this is that corollary 11.2 gives us a way of computing the singular values of a matrix M, whereas Theorem 11.1 for the singular value decomposition has just told us that they exist. To reiterate this, we can compute the singular values of M through the eigenvalues of m star m, namely by taking the square roots of these eigenvalues, and moreover, we can find the matrix V by computing the eigenvectors of the matrix M star M, as we have seen in the proof of Theorem 11.1. And finally, there was also an explicit formula for the column vectors of the matrix U given in the proof of Theorem 11.1. Hence, we have a constructive way of computing the entire singular value decomposition of any matrix M. Moreover, from the proof of Theorem 11.1, it's also straightforward to see what's stated in corollary 11.3. Again, we consider an arbitrary matrix M with rank M being equal to R and U sigma V star being its singular value decomposition. Then we partition the unitary matrices U and V as shown here. So U1 consists of the first R columns of U and U2 of the remaining M minus R columns, and similarly V1 consists of the first R columns of V and V2 of the remaining N minus R columns. This is, of course, the same partition that was already used in the proof of Theorem 11.1. By following the steps in that proof closely, it's easy to see the results stated in corollary 11.3. First, the columns of U1 form an orthonormal basis for the range space of M. Then the columns of U2 form an orthonormal basis for the null space of M star. Moreover, the columns of V1 form an orthonormal basis for the range space of M star. And finally, the columns of V2 form an orthonormal basis for the null space of M. This slide compares the two concepts of eigenvalues and singular values and points out the main differences. First, eigenvalues are defined only for square matrices, whereas singular values are defined for any not necessarily square matrix. Second, the number of eigenvalues, which may possibly be repeated or possibly be equal to 0, is always equal to n, where n is the dimension of the square matrix. The number of singular values, on the other hand, is always equal to r, where r is the rank of the matrix M. Third, in general, the n eigenvalues are complex numbers, unless we're dealing with special classes of matrices, such as Hermitian matrices, where the eigenvalues are real. The singular values, on the other hand, are always positive real numbers for any matrix. And finally, the matrix factorization associated with the eigenvalues is the so-called Jordan form, and the Jordan form reads as T times lambda times T inverse, where the transformation matrix T is a general matrix which is only known to be invertible, and lambda is a square matrix that contains the eigenvalues on its diagonal, and possibly some entries of 1 on the superdiagonal if M is not a simple matrix. The matrix factorization associated with the singular values is the so-called singular value decomposition, and it factorizes the matrix M as U times sigma times V star, where U and V are unitary matrices, and sigma is of the same dimension as M and has a block structure consisting of 4 blocks, where only the upper left-hand block, sigma 1, 1, is non-zero, and this block is in fact diagonal and contains the singular values on its diagonal. In the second part of this chapter, we will look at matrix norms, which will lead us to the concept of an induced norm, which again has a close relationship to the singular values. But before we get to the concept of an induced norm, we first look at a different way to define matrix norms, and that's by considering an m by n matrix simply as a vector in C m times n. By this, we can for instance define the one norm of the matrix A as the sum of the absolute values of all of its entries. Or we can define the two norm of the matrix A, which is also known as the Frobenius norm, by summing up the square of the absolute value of all entries and then taking the square root of this sum. In the same spirit, we can also define the infinity norm of the matrix A as the maximum absolute value of all of its entries. More common, however, is the use of so-called induced norms for matrix norms. These induced norms can be defined more generally for any kind of a linear map. And this is what's stated in definition 11.4. So let L be a linear map from a normed space V to another normed space W. Then the induced norm of L, written here as the norm of L with a little index I, is defined as the supremum over all non-zero vectors in the vector space V of the norm of L of x divided by the norm of x. Here, the norm of L of x is clearly the norm of the codomain W, and the norm of x is clearly the norm in the domain V. According to proposition 11.5, this definition of the induced norm of a linear map, L, can alternatively be written as the supremum over all vectors x whose norm is equal to 1 of the norm of L of x. For the proof of proposition 11.5, note that for any vector x in V without the zero vector, we can define a scalar alpha as 1 over the norm of x and another vector x tilde as alpha times x. Clearly, alpha is a positive real number and x tilde is another vector of the vector space V. Moreover, the norm of x tilde is by definition equal to the norm of alpha times x, which by positive homogeneity is equal to the absolute value of alpha times the norm of x, which by the definition of alpha is equal to 1 over the norm of x times the norm of x, which is obviously equal to 1. Hence, for any vector x in V without 0, there exists a vector x tilde in V with the norm of x tilde being equal to 1 and the norm of L of x tilde being equal to the norm of L of x tilde divided by the norm of x tilde, because the norm of x tilde is equal to 1. And this again is equal to the norm of L of alpha x divided by the norm of alpha x by the very definition of the vector x tilde. Then by linearity of L, we can pull alpha in front of the linear map, and by positive homogeneity, we can pull alpha out of each of these norms such that alpha cancels out, and we're left with the norm of L of x divided by the norm of x. Now, since for any vector x in V without 0, there exists a vector x tilde with norm equal to 1, such that the norm of L of x tilde is equal to the norm of L of x divided by the norm of x, it follows that also the supremum over all such vectors x tilde of L of x tilde must be equal to the supremum over all vectors x of the norm of L of x divided by the norm of x. Two remarks about the definition of induced norms. First, the induced norm does not only depend on the linear map L that we have at hand, but also on the norms defined on the spaces V and W. Then, in case the linear map is given by a matrix in Cm by n, proposition 11.5 reads as the induced norm of the matrix A is given by the supremum over all vectors with norm 1 of the norm of A times x. This fact is of course quite obvious. More specifically, in definition 11.6, we define the so-called induced p-norm of a matrix A, where p is any value between 1 and infinity, or p is equal to infinity, as the induced p-norm of the matrix A being equal to the supremum over all vectors x in Cn without 0 of the p-norm of the vector A times x divided by the p-norm of the vector x. Regarding notation, note that we use the index I to distinguish an induced norm from the corresponding vector type matrix norm. So please make sure that you understand that the p-norm of A is generally not equal to the induced p-norm of A, and that you know the definition of both. Now to some important examples of induced norms. The first one is the induced 1 norm. As it turns out, and this is stated without a proof here, the induced 1 norm of a matrix is given by the maximum over all columns of the sum of the absolute values of the entries of each column. So in short, it's equal to the maximum column sum. Second, the most important induced norm is of course the induced 2 norm. It turns out, and that's again stated without a proof, that the 2 norm of any matrix is equal to sigma 1, which is its maximum singular value. And finally, the induced infinity norm, which turns out to be the maximum over all rows of the sum of the absolute values of each row, which is also called the maximum row sum. Finally, on the last slide of this chapter, we summarize some important properties of induced norms. First of all, induced norms are norms in the sense of definition 5.1. So they satisfy the 3 key properties of a norm: A, positive definiteness, B, absolute homogeneity, and C, the triangle inequality. In addition to that, induced norms enjoy 2 more properties stated in proposition 11.7. A, for any vector x, we have that the norm of L of x is always less than or equal to the induced norm of L times the norm of x. This property is called consistency. And B, the induced norm of the combination of 2 linear maps L and M is always less than or equal to the induced norm of L times the induced norm of M, which is called the submultiplication property. The proof of part A follows immediately from definition 11.4 of the induced norm. The proof of part B will be exercise number 5 on exercise sheet 12.